Hello students and welcome to the lecture. So students, as we know that we are covering the light and so far we have completed the 6 parts of this topic. This is going to be light part 7. I hope that you have revised the previous lectures in the well enough manner before you have come for this lecture. Because you know it's for your own benefit, it is not for my benefit. Okay? So let's see the topics that we are going to cover for this particular lecture. We will see the identification of given light, application and uses of polarization, optical activity, Polaroid, uses of Polaroid, optical instruments, simple microscope or magnifying glass, the camera. So these things we are going to discuss here, starting with the identification of given light, applications and uses of polarization, optical activity, Polaroid, uses of Polaroid, optical instruments, simple microscope or magnifying glass, and the camera. So this is going to be a very informative lecture, so please be attentive here. But before we start the actual lecture, there is a small disclaimer that we are required to understood first before we proceed further. So the disclaimer goes like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this tag and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now let's begin with the topic. So how do we identify the given light? So we will see this in the identification of given light. So let's start. Polaroid or Nicol prism is used to examine whether a given light is unpolarized, partially polarized or plain polarized. So for three purposes we use the Nicol or Polaroid or Nicol prism to see whether the light is unpolarized, partially polarized or plain polarized. For this, the given light is passed through a Polaroid that we called as an analyzer, because after the activity of this passing a light through the Polaroid, we will analyze the things. So that's why it is often what we call as an analyzer. And the Polaroid is rotate about the incident light and emergent light is same. Then if so, we know we pass the light through a Polaroid, then we rotate about the incident light and emergent light is observed or seen by us. Then there are the following conditions that we could have. First, there is no variation in intensity of emergent light in any position. The incident light will be unpolarized. As in the case of unpolarized light, the vibration of same amplitude are equally probable in all directions. So if we see the intensity of incident light and the emergent light is not having any variation with any position, then we could say the incident light that we pass through that Polaroid is actually unpolarized. Why? Because in the case of unpolarized light, the vibration of same amplitude are equally probable in all the possible directions. Second case, there is variation in intensity of emergent light with minimum not equal to 0. The incident light will be partially polarized, as in partially polarized light vibration exists in all direction but the move in some direction than in others. Okay, so here we could say, if we talk by the variation in intensity of emergent light, and now we having a minimum not to equal 0. So we could say if we having a variation with minimum but these are not 0, then we could say the incident light that we pass through a Polaroid is actually partially polarized. Why? because in the partially polarized light, vibration exists in all directions, but they move in some directions than in others. Third case is there is variation in intensity of emergent light with minimum equal to 0. The incident light is plane polarized, as in plane polarized, the light vibrations are confined along one direction only. And so, transmission axis of analyzer will become parallel and perpendicular to vibration twice in its one complete rotation, giving rise to the maximum and zero intensity twice in each rotation. So these are the three cases that we observed while when we use the Polaroid, that we also called as an analyzer. Okay, and by seeing the variations in the intensity of emergent light and the incident light, by applying some cases, we could tell whether the light is unpolarized, partially polarized, or plane polarized. Okay, now let's move ahead. Application and uses of polarization. So, by determining the polarizing angle and using Brewster's law, therefore, mu equals to tan theta p, the refractive index of dark substance could be determined. It is used to reduce glare, which is due to the horizontal polarization of light by reflection from ground or water, etc. By wearing Polaroid sunglasses with vertical transmission axis. In calculator and watches, number and letters are found by liquid crystal through polarization of light that we call the liquid crystal display or LCD. You know about it. Like mostly nowadays we use the LED light emitting diodes. Prior to this, if we talk about the smart TVs that we usually use at our homes, we had the liquid crystal display LCDs. Okay, nowadays we use the LEDs. So basically, the LCD is also based on the polarization of light, because the liquid crystal through polarization of light we use to form the numbers and letters that are shown on there. Thereafter, in CD player, yani, what we call as a compact disc, polarized laser beams act as needle for producing sound from compact disc, which is an encoded digital format. So, have you ever wondered like how the sound produced in the CD? Because it is in the encoded digital format. So for this, we actually use the polarized laser beam for the CD player. Here you can see this picture. And this is actually acting as a needle to produce a sound from the compact disc. And the sound is already presented in the CD or the compact disc in the encoded digital format. It has also been used in recording and reproducing three-dimensional pictures. Nowadays, 3D pictures are recorded and reproduced holography using laser. Polarization of scattered sunlight is used for navigation is solar compass in polar regions where magnetic compass becomes inoperative. So basically if we talk about the magnetic compass, so we could easily use them over the earth, but the cases of poles having the different implications. Like near the poles, the earth gravitational pull is totally vertical and high. So that's why the needle of the magnetic compass becomes inoperative in that cases. So that's why we could say overall that magnetic compass are not effective while using in the polar regions. So if the magnetic compass are not in the workable condition, so what we should use in place of them, we use the solar compass to show the directions and the current position of object or a person with whom the compass is present with. So here we use the polarization of scattered sunlight for this particular navigation purpose. Polarized light is used in optical stress analysis known as photoelasticity also. Polarization is also used to study asymmetrics in molecules and crystal through the phenomenon of optical activity. Now, What do we mean by the optical activity? Let's have a discuss on this also. So when a plane polarized light passes through certain substances, the plane of polarization of light is rotated about the direction of propagation of light through a certain angle. This phenomenon is what we call as a optical activity or optical rotation. Why? Because here the plane of polarization of light is actually rotated in the direction of propagation of light with certain angle. We couldn't say any angle, we say certain or specific angles. So that's why it is also known as optical rotation, or commonly we call it as an optical activity. The substance is optically active. If they are not optically active, they will not be able to give us this optical activity or optical rotation that easily or even by any way. If the optically active substance rotates the plane of polarization clockwise, that is looking against the direction of light, okay, it is said to be dextrorotatory or right-handed. Dextrorotatory in case of clockwise polarization in the direction against the direction of the light, okay. Whereas if the substance rotates the plane of polarization anti-clockwise, then it is what we call as the levo-rotatory or left-handed. The optical activity of a substance is related to the asymmetry of the molecule or crystal as a whole. Example that we could take: a solution of cane sugar is dextrorotatory due to the asymmetrical molecular structure, while crystal of quartz are dextro or livio rotatory due to the structural symmetry which vanishes when quartz is fused. Optical activity of substance is what we measured with the help of polarimeter in terms of specific rotation. Now, Polaroid. So, Polaroid are thin and large sheet of crystalline polarizing material which are made artificially, and they are capable of producing plain polarized beam of large cross section. There is a note: a nickel prism or a tourmaline crystal, natural polarizing material, couldn't be used to produce plain polarized beam of light of large cross section. That is an important note. Why? It is because of the reason that very large crystals of calcite and tourmaline are not available in practice. That's why it is not possible. They are only the artificially made or thin and large sheets. In 1852, Haripet discovered that the synthetic small needle shaped crystal of quinine isosulfate having the property of polarizing the light. Their crystals are called herpetite. These crystals are actually not stable and couldn't bear even a slight strain, which means that if they got strict with anything, they will be break easily. Since such crystals couldn't be used as such, a Polaroid sheet is prepared from the suspension of these crystals in nitrocellulose. So what we do? We suspend these crystals in the nitrocellulose. So that's how we prepared a Polaroid sheet. To impart stability, its thin sheet is mounted between the two sheets of glass or celluloid. Each Polaroid sheet is enclosed between the thin glass plates so as to provide the mechanical support. So that's why they should not be break while doing the activity. Thereafter, we could say a polarized sheet could also be obtained from a sheet of polyvinyl alcohol. When such a sheet is subjected to a large strain, the molecules get oriented in the direction of applied strain. When the sheet is impregnated with iodine, the material becomes dichroic. The Polaroid sheet so obtained is called H Polaroid. If the stretch sheet of polyvinyl alcohol is actually got heated in the presence of dehydrating agents such as HCl, hydrochloric acid, it actually becomes strongly dichroic as well as very stable. Such a Polaroid sheet is called what we call as the K Polaroid. Now, what are the uses of Polaroid? So the Polaroids are widely used, and a few important uses are as we listed below. In sunglasses, Polaroids are used in sunglasses. Such goggles are more efficient than those mode of colored glasses. They protect the eyes from the glare. Second use is in windshields of automobiles, like here you can see. These are the windshields of automobiles. Here you can see the Polaroids. Okay. Such a windshield protects the eyes of the driver of the automobile from the dazzling light of the approaching vehicles. For the same reasons, the covers of headlights are actually made of Polaroid. Now the window panes. The Polaroid is also used in window panes of a train and especially of an aeroplane. They help to control the light that is entering through the windows. Thereafter, in three-dimensional motion picture, the picture taken by a stereoscopic camera, when seen with the help of Polaroid spectacles, create the three-dimensional effect. Polaroids are used to improve color contrast in old oil paintings also. Now, in calculators and watches, letters and numbers found by liquid crystal display through the polarization of light. In CD players, polarized laser beams actually act as needle for producing sound from the compact disc, which is in encoded digital format. Now, the polarization of scattered sunlight is used for navigation in solar compass in polar regions where magnetic compass becomes inoperative, the reason I have already told you. Polaroids are also used in optical stress analysis. By determining the polarizing angle, IP, and using the Brewster's law, refractive index of dark transparent substances could be determined. Polarization is also used to study asymmetrics in crystals and molecules using the phenomenon of optical activity. The microscope's objectives actually fitted with Polaroids to avoid the glare in observing very minute particles. Now, what are the optical instruments? The optical instruments are the devices which actually help the human eye. First, in observing highly magnified images of tiny objects for detailed examination. In observing very far off objects, terrestrial or astronomical. Microscope and telescopes are common examples of optical instruments. Simple microscope or magnifying glass, what is the difference between them? So, a single microscope is used for observing magnified images of tiny objects. It consists of a converging lens of small focal length. A virtual erect and magnified image of the object is formed at least distance of distinct vision equals to 25 centimeter from the eye held close to the lens. That is why the simple microscope is also called magnifying glass. Now, magnifying power, let's have a talk on this. The magnifying power of a simple microscope is defined as the ratio of angles suspended by the image beta and the object alpha on the eye when both are at least distance of distinct vision from the eye. Thus, the magnifying power is m equals to beta by alpha. For a simple microscope magnifying power, when image formed at the least distance of distinct vision, m equals to 1 plus d by f, where d equals to least distance of distinct vision, 25 centimeter, f equals to focal length of simple microscope. As f decreases, m increases, therefore smaller the focal length of lens, greater is its magnifying power. If the eye is placed behind the lens at distance d, then m equals to 1 plus d minus d by f. Here 1d is capital, another one is small. When image formed at infinity, m equals to d by f equals to 25 by f. Therefore, d equals to 25 centimeter. Uses, if we talk about it, by watchmakers and jewelers for having magnified view of tiny parts of watch and fine jewelry work. By students in science laboratories for reading vernier scales, etc. The image is very bright and sharp because object is held close to the lens. Note, the world's most powerful microscope is now ready. It could see things at magnification up to 20 million times larger than the human eyes could see. This 4.5 meter microscope called scanning transmission holography microscope could see atoms. The end result of this microscope will be the development of new technologies from computers to medicine and alternative energy to make devices which actually smaller, faster and better with large memories. Now, what is the camera? Let's have a talk on this also. So the camera is actually used to obtain a permanent image of an object on a photographic plate or film. The photographic camera consists of a light-proof box at one end of which a converging lens system is fitted. A light-sensitive film is fixed at the other end of the box opposite to the lens system. A real inverted image of the object is formed on the film by the lens system. For a good photograph, the amount of light entering the camera has to be adjusted accurately. Following controls are provided in the camera for this purpose. Let's see the controls. Shutter. Shutter is placed between the lens and the film. When a photograph is to be taken, the shutter opens for a suitable time and closes quickly. The film is thus exposed to light from the lens system only for the calculated time. Exposure time. This has to be adjusted according to the light conditions. In bright sunlight, exposure time has to be small. In shade or inside the room, the exposure time has to be larger. In cameras, exposure time controls carries the marks like 500, 250, 125, 60, 30, 15, etc. Here you can see this one. This means that when the time control is adjusted against these marks, the light entering the camera will be cut off after 1 by 500 second, 1 by 250 second, 1 by 125 second, and so on respectively. Aperture control. By this, we adjust the diameter of the circular opening through which light passes into the camera. In bright sunlight, a small aperture may allow enough light to produce a good image. But the poor light conditions, the aperture has to be made large. The aperture control bears the marks 2, 2.8, 4, 5.6, 8, 11, 16, etc. These are called f number, where f is the focal length of the converging lens system of the camera. The numbers thus correspond to the aperture of diameter f by 2, f by 2.8, f by 4, f by 5.6 and so on respectively. Note that the numbers 2, 2.8, 4, 5.6, 8, 11, 16 actually obtained by a successive multiplication by a factor. Note, let x be the distance of far point of myopic eye and f be the focal length of concave lens to be used. Now for concave lens, u equals to infinite and v equals to minus x. As 1 by f equals to 1 by b minus 1 by u, or 1 by f equals to minus 1 by x minus 1 by infinite, or f equals to minus x. Hence, focal length of concave lens put in front of the eye should be equal to the distance of far point of the defective eye. So here we have finished this lecture. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.